Suppose a manufacturer of steel shafts is producing shafts of length 200 millimeters to supply to a producer of electric motors. The production process imposes a standard deviation of 10 millimeters on all shafts produced at this facility. The manufacturer expects some variability in the lengths of the individual shafts produced. The contract specifies that the shafts must be an average of 200 millimeters in length. The contract also specifies a tolerance that there must be a minimum average length of 195 millimeters. If the machines wear to a point that the shafts produced reach this minimum average length, then he must stop production, partially dismantle the machine, and replace some parts. Each day, the manufacturer draws a random sample of 35 shafts and measures them. At the 0.05 level of significance, find the probability that he would detect a true population mean of 195 millimeters. So, the hypothesized mean is 200 millimeters. This is what is specified in the contract, that the population mean is 200 millimeters. So this would be the null hypothesis, our hypothesized mean. The contract specifies that there must be a minimum average length of 195 millimeters. So alpha is going to be down here in the left tail. Now we're told that the production process itself imposes a standard deviation of 10 millimeters on all shafts produced. So that would be a population standard deviation. This would dictate then a critical Z value. And this critical Z value would be minus 1.645. And we can use the TI-84 calculator or a table or StatCrunch or any utility that we want to find that critical Z value. Now the question asks us to find the probability that he would detect a true population mean of 195 millimeters. Now this is what the mean is supposed to be, but unknown to this manufacturer, the population mean might actually be 195 millimeters. Now what we should do at this point is find the sample mean that would get us all the way down here to minus 1.645 if we calculated its associated z-test value. So what is this sample mean? Well, we know from the z formula that we would subtract the population mean, or the hypothesized population mean, from the sample mean, and then divide that by the standard error, which is the standard deviation divided by the sample size. Well, we know what this z value is here. We're looking for the sample mean associated with that z value, or that corresponds to that z value. So we would know this value, we would know our hypothesized mean, we know our standard deviation, and we know our sample size. So this formula would also then, if we rearrange it a bit, would give us our sample mean. And doing a little algebra on that, we would find that that sample mean would be found by multiplying z by the standard error, and then adding to that the hypothesized mean. So if we do that, we're going to wind up with minus 1.645 times 10 divided by the square root of 35, and then add to that 200. And that value will turn out to be 197. Now the population mean is supposed to be 200 millimeters, but we know that after the machine's wear, this actual average can diminish, and if unknown to the manufacturer, the population mean has gotten to the point where these shafts measure an average of 195 millimeters, then the distribution would actually be different from what is hypothesized. 195 millimeters would be down here to the left of 200. Now, this value corresponds to a sample mean of 197 millimeters, which is to the right of 195 millimeters. So if this then is the actual population mean, then this is what our distribution would look like. And the probability that we would detect that true population mean would be the same as this area to the left of this critical value, this corresponding critical value here. So what we're going to call this then is mu sub 1. So that is then the actual mean. And here we have our sample mean of 197. So the probability that we would detect this mean of 195 millimeters would be the same as this area here. We would find that by calculating a z-value. So our z-value now is going to be same formula. This time we're going to have 197 minus 195 divided by 10 over the square root of 35. And the result is 1.18. And if we use StatCrunch or a TI calculator or a T-table or a Z-table or any other utility, we're going to find that this area right here is 0.8810. And that's all the way from this value of 197 all the way out. Now, that probability there, the probability that we would detect a true population mean of 195 millimeters, is called the power. The power is 0.8810. Something else that we can answer from this value is the probability that we would commit a type 2 error. Since the power and the probability that we would commit a type 2 error are complements, then this probability would be 1 minus 0.8810 or 0.1190. So that's this area in here. Now, if we think about that and match it up to our picture up here, this hypothesized mean is what we are supposing. We're supposing that this mean is 200 millimeters. That two errors that we could commit in hypothesis testing are a type 1 error, where we reject a true null hypothesis, which corresponds to alpha. The other error is beta, the probability of committing a type 2 error. A type 2 error would be to fail to reject a false null hypothesis. So all of this area through here would represent where we might land if we don't reject the null hypothesis. So anywhere through here, if we land anywhere to the right of this critical value, we would not reject the null hypothesis. And if the null hypothesis is false, then landing in that area would cause us to commit a type 2 error, failing to reject a false null hypothesis. If we fail to reject the null hypothesis and the actual mean is 195, then that area corresponds to this area here, which again is beta, or the probability of committing the type 2 error. That leaves this area here to be the power, 0.8810.